building, a heating, surrounded by a shell. The heating produces heat which disappears fast or less fast through the shell outside. The U-value theory describes a model at which the inside of a shell is warm, for example, 20 degrees Celsius, and the outside cold, for example, -5 degrees Celsius. In between the outer shell, the temperature difference between inside and outside is called the temperature gradient, which is more or less the barrier between the heat flow from the inside to the outside. The U-value approach is simple and logical. If the U-value is high, the heating costs are high. If the U-value is low, the heating costs are low. So in order to get the lowest U-values, the heat resistance of the shell has to be improved. Subsequently, the energy consumption falls. These things may occur when an additional layer of insulation is added to the existing facade, or if during building, construction materials are used that offer better insulation value. However, this model has a problem, the so-called hyperbolic problem. Because the U-value is, as we all know, a formula, a mathematical formula. In the case of insulation of a building, an insulation value improvement by 100% does not lead to a U-value reduction by 50%. That's a mathematical law. What is that U-value, in fact? This is the heat transfer coefficient. So the extent of the heat transfer of room air via the wall toward the outside air is based upon the difference in air temperature. The U-value is the reciprocal. So it is the reversed value of the heat transfer coefficient. This heat transfer coefficient of the wall is built up by the resistance of both inside and outside. Of course, they are DIN standardized, and they are marked as steady. The wall consists of independent layers of construction material which are specified by their thickness and value of heat conduction. For most of the buildings without insulation, the U-values of 1.2 are known. Closely related to the U-value is the lambda value as a size for heat conduction. For example, metal conducts heat better than wood. Construction materials have different lambda values. Concrete, which is robust, offers a very good heat conduction with lambda equals 2 to 3 WMK and is therefore not suitable for being an insulation material. The lambda value of EPS, known as polystyrol, was developed from 0.040 via 0.035, 0.032 to 0.028. In laboratories, the lambda value, as a building physical standard, is measured under steady conditions. In a so-called plate box, the heat flow is measured between a hot and a cold plate. And of course, the circumstances such as temperature and humidity are steady in order to compare results. So far for theory and standard. Unfortunately, reality looks a little different, as anyone who looks outside will recognize. Rain, wind, and sun create changing circumstances for the building envelope every day. Additionally, residents breathe, take showers, and cook. Moreover, the weekly times and seasons have to be added. The value from the lab with standardized conditions and steady calculation values shows a predictable but unclear image of practice, and has been by others deeply explained in the Galvin study. In this study, smaller savings, average 40% to 50% less, were found than of which was calculated through the official simulation programs. However, it annoys that despite from this database, the insulation is emphasized continuously. 3 inches is passed, 6 inches is standard, and 12 inches is widely promoted. Despite the hyperbolic problem, and despite the build physics effect, that does not show any constant result. in 2009, a project in the Swedish town of Botkyrka was guided by an independent institute. A thermoceramic membrane was used as a wall paint to an existing facade. The measurements, which were produced by one of the largest energy advisors in Sweden, showed an energy saving by 15% and more in comparison to non-renovated facades. Here, big buildings are at stake, and that's why we may conclude that the results are representative as a result of low variance. We are talking about just a 0.3 millimeter ceramic coating, which has been applied to the facade. Another example from the Austrian Kaffenberg. In 2011, this house was painted with ThermoShield exterior. The savings of this building were not very high, 10%. However, neither are the costs. An external wall insulation would have cost about $500,000 for this building. However, the professional paint job took less than 1/3 of that price. At a building in Jonava, Lithuania, the same professionally applied ThermoShield facade coating led to an energy saving of more than 14%. The saving that may be realized with an external insulation bonding system vary widely, depending upon the provider and those interested. The independent German institute Heispiegel comes with current comparison values. However, with a saving potential of only 12% in case of afterwards installed insulation systems. Sources near the producers speak of 20% and more. The U value does not explain what happens on these buildings. Despite a seemingly non-existent U-value improvement in the thermoceramic membrane in a thickness of just 0.3 millimeters, demonstrably 1/1000th of what is required in the near future by the official energy savings guidelines, it shows a proven saving result. Perhaps this answer is helpful. The U-value is a computing model that arises from lab values. Wind, humidity, and the sun are not really taken into account. The U-value is a tool to classify external thermal insulation systems, not less and not more. However, a thermoceramic membrane is no insulation, but something completely different. It does not work as an insulation, however, it changes the characteristics of the building envelope. A thermoceramic membrane has a direct influence on the humidity of the building envelope. The membrane uses solar yields which appear on the building envelope to dehumidify, control the temperature, and evenly distributes heat to the surface. Practice studies have been proven all throughout Europe. If you face the considerable insulating material thickness of 12 inches, a facade coating like ThermoShield with a thickness of 0.3 millimeters shows a ratio of 1 to 1,000. After the U-value theory with zero effect, but nevertheless proven by many empirical examples in practice to significant energy savings. Now, a way has been found based on sufficient evidence to enable conventional official energy calculation programs to implement the ThermoShield calculation options. For this purpose, just the calculation factor FTS must be inserted in the by scientists adapted U-value formula. Here's the mix of the physical effects created by the complex effect of the four components such as membrane effect, emission, reflection, and scattering, and a positive energetically conductive behavior on the building envelope. If you have any questions about this topic, please contact us directly. We will inform you about the products of ThermoShield and reply to any further questions.